Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been discussing about various oligomerization of olefins and alkyne reactions, and in this context we have looked at the first and the foremost of this type of reaction, which is shell higher olefin process in great detail, and look at SHOP from the context of olefin oligomerization giving alpha alkenes. Now, this SHOP process was a very important process which was practiced in industrial scale for producing detergent, and this primarily had its origin for making alpha olefins for applications in surfactant and detergent, and these initially were obtained by cracking of crude oil. However, later as Ziegler-Natta catalysis evolved, nickel catalyst was found which could produce alpha olefins from C oligomers from C to C3 all the way to C20 and above. The only drawback about this olefin oligomerization under in SHOP process was that this Ziegler-Natta type coordination insertion olefin oligomerization was non-selective, in the sense that it could produce a bunch of oligomers with various distribution ranging from smaller oligomers of dimer trimer to large oligomers having more than 18 or 20 monomer unit. Now, in order to make use of this large distribution of oligomers, two other process, for example, olefin isomerization followed by olefin metathesis, they were put in place to make use of the low molecular weight oligomers as well as high molecular weight oligomers, which individually had not much use as detergent. So, this is a combined SHOP is a combined process that involves alpha olefin oligomerization, isomerization and metathesis put together to make crude material for producing detergents. So, we have covered this in great detail in our previous lecture, and also we have looked into the alpha olefin oligomerization catalytic cycle, and the thing that comes out is that that the active species is usually a nickel hydride species. The active species also what has been observed is change of solvents. Gives high molecular weight higher molecular weight, linear oligomers, and this was done in the solvent is, for example, hexane. Lastly, for the shop process, what was found that addition of triphenylphosphine gives chain termination. For example, 1 butene is obtained. So, even though this was oligomerization of olefins was a very useful process which helped develop this shop process altogether. However, criticism again of this process lies in its lack of selectivity, because a large numbers of oligomers of various chain lengths are obtained at different ratios during the process of alpha oligomerization using the nickel catalyst. So, selectivity was itself issue. Now, in this context, another important example needs worth mentioning is about ethylene trimerization of ethylene. Now, so the process indicates conversion of ethylene to 1 hexane. Now, the process is important with respect to alpha olefin production or oligomerization in shop is with regard to the selectivity of this reaction. So, this reaction is highly selective in terms of producing 1 hexane. And now, this discovery has a Indian impact on it and is made by the group of Professor Ayushman Sen, and has been reported by Professor Ayushman Sen of Pennsylvania State University. And it was reported in Journal of American Chemical Society. In 2001, very recently in that 123. So, one beauty about this reaction is the selectivity. Highly selective as compared to the alpha olefin produced by olefin oligomerization during shell olefin process. And interesting thing to note over here, that for this reaction an early transition metal tantalum, a tantalum catalyst has been used, as opposed to nickel catalysts which are often used for producing alpha olefins from ethylene oligomerization reaction. Now, this to be more precise, titanium pentachloride is the starting precursor in presence of some metal alkyls. MRN and these metal alkyls can become can be several alkylating reagents like trimethyl aluminum, tetramethyl 10, dimethyl zinc, and N-butyl lithium. So, this the scope of this reaction in terms of generating the active species is very broad, where different types of alkylating reagent like trimethyl aluminum, tetramethyl zinc, dimethyl zinc, butyl lithium are used to alkylate this tantalum 5 compound, tantalium pentafluoride, to get the active species, which is actually a tantalium 3 species. So, let me this is a very interesting discovery, which has the mark of an Indian inventor, Professor Ayushman Sen, currently on roll in Pennsylvania State University, who had made this fine discovery. So, let me just walk you through the catalytic cycle for this trimerization of ethylene reaction. The first is the formation of the active species, which is the active species is suggested to be a tantalum 3 species. Is a tantalum 3 species, and this active species is produced from tantalum 5 compound precursor, as is shown below. In presence of M alkylating agent, gives Cl3 tantalum dimethyl. So, its partial alkylation that occurs of the tantalum 3 species. So, penta 5 becoming 3 chloride and 2. So, this is partial alkylation which occurs to get this tantalum 5 species. Then that reacts with ethylene to give tantalum methyl ethyl species, where the coordination insertion of coordination of the ethylene occurs on one of the tantalum 5 tantalum methyl bond to produce this tantalum propyl moiety. Now, this tantalum propyl moiety, because of electron deficiency of tantalum, has beta hydrogen, which sort of beta eliminates to produce this tantalum hydride methyl species with coordinated propylene. Now, then under this ethylene bound tantalum hydride species, undergoes a bit reductive elimination as is shown over here. To eliminate methane as well as propene. Propene to generate the active species with which is a tantalum trichloride. So, this is the active species, active catalyst for ethylene trimerization. One thing to note about this catalyst is that this species is both sterically unsaturated as well as electronically unsaturated. So, this is a 8 electron species and this is sort of 3 coordinate 3 ligand. So, this species is highly active in terms of having very less of steric saturation, only 3 chloride ligands bound to titanium, and also electronically very unsaturated because it is a 8 valence electron, 3 from chloride and 5 from tantalum. So, it is a 8 valence electron species. So, it is also very electronically unsaturated, and this is supposed to be the active species for this catalytic hexene trimerization reaction. So, one beauty about Huysman-Sen's work is that he has successfully demonstrated the use of an early transition metal like tantalum for producing olefin oligomers like 1-hexene. Usually the common wisdom had been that early transition metal produces high molecular weight polymers, whereas more electron rich late transition metals produces oligomers. But here we have a nice example from Sen's group where he had successfully used an early transition metal for producing trimers of ethylene in form of 1-hexene. The second important feature about Sen's work is the selectivity that in olefin oligomerization using neutral catalyst in SWAP process, a wide range of alpha olefins bearing different chain lengths are produced, whereas Sen has showed that a highly selective trimerization can proceed with his catalyst that only gives 1-hexene as the final product. So, these two are the key features that sort of separates or that sort of separates Sen's work from the existing catalyst, or which sort of shows superiority of Sen's work from the existing catalyst which had been known for olefin oligomerization. So, now we are going to take a look at the mechanism as to how these active species tantalum tetrachloride carry out this trimerization of olefins, ethylene. tantalum trichloride, which is highly sterically unsaturated as well as electronically unsaturated. Reacts with 2 molecules of ethylene to form this tantalum metacycle, pentacyclic metacycle. So, this is quite stable and is also has been shown by DFT calculation by others that this is a stable or stable product which will eventually form from 2 olefins. Now, the species which is formed is tantalum 3 Cl3 tantalum metacycle, where the oxidation state of tantalum has again increased from tantalum 3 to tantalum 5, and this is a sort of an oxidative reaction which occurs, oxidative addition which occurs by addition of 2 ethylene molecule. And can be seen as such. Tantalum 3 and 2 species with tantalum donating electron onto the ligand to form this tantalum metacycle, which is shown over here. Subsequently, the reaction of another olefin happens by coordination insertion pathway to give to this tantalum 7 membered ring, and this happens by simple coordination followed by insertion of this into the bond to give that 7 membered pathway, and finally the reductive elimination to generate back via to generate back this tantalum 5 membered compound via beta hydrogen elimination this going to this, and that undergoes going reductive elimination, giving 1 hexane as the side product. So, this also involves reductive elimination. So, what is happening over here, one can see that this catalytic cycle initiates with oxidative addition and then tantalum becomes 4 and then goes to reductive elimination, where again the tantalum oxidation state changes from tantalum 5 to tantalum 3. So, this is a very nice piece of work by Professor Sen, where one could see that a tantalum 3 species being generated in the course of the reaction, and that is a highly electron deficient as well as highly unsaturated compound, which then successfully carries out this trimerization of ethylene to give 1 hexane, first by oxidative addition of 2 ethylene molecules to give a tantalum 5 species, which also then further undergoes one more insertion to give a 7 membered metal cycle of tantalum, and that finally beta hydrogen eliminates as well as reductively eliminates to give 1 hexene as the product and regenerating back the titanium trichloride. So, with this I come to the conclusion of today's lecture, in which we have looked into first the various important attributes of olefin oligomerization, particularly from the perspective of its active species, which is the nickel hydride species, and the effect of solvents, for example, on going to solvents like hexane, higher molecular weight polymers are obtained, or the effect of addition of phosphines, which sort of allows chain termination and facilitates lower oligomer formation. And the second aspect that we have discussed is about interesting reaction that involves highly selective trimerization of ethylene to 1 hexene, and this has been reported by Professor Ayushman Sen of the Pennsylvania State University in the JSCS article 2002 article, which we have already referred to, and request the reader to read it with more detail. And in this, Professor Sen has very nicely demonstrated that even against the conventional wisdom, that even an early transition metal can be used for successfully used for olefin trimerization in a very selective fashion. In particular, he have started with the tantalum pentachloride using some alkylating agent. He had generated a highly unsaturated and highly electron deficient tantalum 3 species, which selectively produces 1 hexane in the mechanism as is shown below. So, very interesting work, and it also highlights the scope of organometallic chemistry, particularly in terms of carrying out very different kinds of transformation, some of which may even go beyond the wisdom of the conventional logic. And nice work by Sen in this regard was discussed. So, with this I come to the conclusion of today's lecture on ethylene oligomerization and ethylene trimerization that we have discussed. We are going to talk more on few more other examples of various kinds of olefin oligomerization reaction when we meet next in this lecture series. Till then, thank you and goodbye.